In last two videos we finished engineering mechanics, all the questions of RS Kurmi. Okay, what I will do in my channel, I will provide all the RS Kurmi, RK Jain, IES direct question and GATE 1 mark question and 2 marks question, match the following the type of questions. All the questions I will provide you, and this much is enough for clearing any PSU or any PSU, state government, railways, any exam. So what you have to do, you have to read these questions from these books first, and after that you have to see the videos before 10 days of your exam, or whenever you get the time. What will happen, so you already know the answer. Just whenever before I will mark the answer, you have to see the what is the answer, so you have to memorize your answer. So before I will mark, so you have to say your answer, so it will be become like a test for you. So already in my channel I provided in the all the engineering mechanics questions in two parts. I finished like this, but in this strength of materials, total questions are 480 is there. So in three parts I will provide this one. So today we'll gonna see first part. So one part is 160 questions will be there, 160, 160, 160, three parts. So total 480 questions will be there. Like this all the subjects will finish. Okay, so now we're going to see strength of materials. So you can see here the strength of materials. So here some definitions are there, but we are going to do only the questions. So if you have any doubt, you can in the comment section you can comment. I will provide you the solution for those questions. And now we're going to see the first question. Okay, so before I will mark, you have to mark your answers. Okay, the unit of stress in SI units. The units of stress in SI units is Newton per mm square, kilonewton per mm square, Newton per mm square. So it is all of these above. It's all of these above. Any one of these above. The deformation per unit length. Deformation per unit length is called yes, you are correct. So deformation per unit length, it is called strain. Okay, next. Okay, we missed the first question here, sorry. Whenever some external system of forces act on a body, it undergoes some deformation. As the body undergoes some deformation, it set up some resistance to deformation. The resistance per unit area. See, stress means internal resisting force. So this is the correct answer. Resisting for unit area. This is the stress. Stress is equal to force by area, and this area is resisting area. Okay, so this much you have to understand. So you have to tell your answer before I will mark. Okay, so that it will be like a test for you. The unit of strain is, strain doesn't have any units. The strain is equal to delta L by L, change in dimension by original dimension, that is delta L by L also we can write. When the body is subjected to two equal and opposite pushes means like this, then what will happen, this is the rubber, then what will happen, it will reduces its length, yes, and stress and strain produce are compressive because they are coming near together. If opposite pull, same it is there, but now you are doing pulling, then what will happen, this one will length will be increases and the tensile stress and strain will develop. Okay, next. When a body is subjected to two equal and opposite forces acting tangentially across, so tangentially across the, like this, tangentially across the resisting section, as the result of which body tend to shear off across the section, the stress and strain produced, strain induced is shear stress and shear strain. So this is the rod. So here some in this direction one and the opposite direction one stress is coming, force is getting, then the resulting force is shear stress and shear strain you will get. So it is tangential to this longitudinal axis, these forces are. Which of the following is a proper sequence? So in the stress strain curve, if you see the mild steel stress strain curve, so proportionality limit, elastic limit, upper yield point, lower yield point, ultimate stress and breaking stress. Okay, these are the points you will get. So proportionality limit, elastic limit, yield point and failure point. Okay, this is the correct. Hooke's law holds goods up to actually proportionality limit, but its proportionality limit is not given. And the next point is elastic limit you have to consider. Whenever the material is loaded within the elastic limit, stress is directly proportional to strain according to Hooke's law, but actually that is proportionality limit. The ratio of linear stress to linear strain is called modulus of elasticity. So E is equal to stress by strain. These are the linear stress by linear strain. The unit of modulus of elasticity is same as that of a stress, pressure and modulus of rigidity, because it's here you can see the strain doesn't have unit, so Young's modulus is same as that of a stress or modulus of elasticity. Young's modulus is also as a modulus of elasticity. Next, when a change in length takes place, the strain is known as change in length, so that is called as a linear strain. The change in length due to tensile or compressive force acting on the body is given by, so E is equal to stress means stress by strain. Stress means stress by strain. Stress means P by A by delta L by L. So L will go in the numerator, delta will come here. So PL by delta L into A. So from here E is equal to PL by delta L by A. So A will go here, E will come, delta L will go here, cross multiply PL by A into E. So delta L is equal to PL by A into E. So this is our answer. Okay, got it now? Like this. The modulus of elasticity for the mild steel is approximately equal to this value. You have to remember. No trick for this. Just remember 210. Young's modulus may be defined as a linear stress to linear strain. Young's modulus means basically modulus of elasticity only, linear stress to linear strain. Modulus of rigidity may be defined as a shear stress to shear strain, that is indicated with G, and Young's modulus is indicated basically with E. Next, the units of Young's modulus is same as that of a stress. Yes, correct. Okay. Two bars of different materials have the same size are subjected to the same tensile force. If the bars having the elongation in the ratio of this one, their modulus of elasticity. So just now we see delta L is equal to PL by AE. So delta L means change in length and E is Young's modulus. The modulus of elasticity, these are inversely proportional. So delta L1 delta L2 is E2 by E1. But here delta 1 by delta is 2 by 5 is given. So E2 by E1 is 2 by 5. So E1 by E2 is, it is reverse, 5 by 2. So 5 is to 2. When a bar of length L and diameter D is rigid fixedly at the upper end like this, it's fixed and hanging freely, then the total elongation produced in the bar, its own weight. You have to remember this question, they will ask you. So WL square by 2E. How will get? So the own weight, how much will be there? Actually capital WL by 2AE is the elongation produced by the body, its own weight, delta L. So but this capital W is total weight. So unit weight will consider WA, small WA into L. When you substitute here, this A and this A will cancel. So W into this L and this L square. So WL square by 2E. This is small w. Okay, this is small w. Small w means per unit weight. So that's why weight per unit volume. Yes, sorry, unit volume. That is a small w. Deformation of bar under its own weight is dash the deformation if the same body is subjected to the direct load. Direct load equal to the weight of the body. It is half because WL by 2AE, capital WL by 2AE is the normal weight when a self weight, but normal is WL by PL by AE, that is the without self weight. Means if you considering a here some weight is acting W, so this condition, this is without this is, so then this is a half of this, the second case. So it's a half of this second case. A conical, the elongation of conical bar under its own weight is 1/3 of the prismatic bar of the same length. So this is the 1/3 of WAL by 3 will be there in place of capital W. Okay. Next. So 23rd till 23rd we finished. So in this video we will finish total 160 question. Next video 160. The conical bar of length L and diameter D in the weight per unit length is W. It's fixed at upper end and hanging freely. The elongation of bar under its action of the own weight will be. So conical bar it said. So already I told you normally WL by 2AE is there, our self weight elongation. This capital W in this conical bar case W small w AL by 3. If it is prismatic bar, then it is WAL by WAL, just WAL. So AA will cancel. So WL into this W L. So WL square by 3 to the 6E. So WL square by 6E. Strain rosettes are used to measure the linear strain. Okay. A bar of length L meter extended by 1 mm under the tensile force P. The strain produced is. So this is the bar. Initially this much is there. Now this much is increased. So this is small L mm. This is capital meters. So this 1 L mm is mm you have to convert into meters. So delta L by L. So delta L is L mm. L mm is 0.001 meter L small l by capital L meter. So this meter will cancel. So 0.00001 L by 001 L by capital L. So 0.001 L by capital L. So now here is a conical bar tapered, a circular bar tapering uniformly from diameter D1 at one end to D2 other end. The subject to axial pull P is given by the 4PL by pi D1 D2 into E. So this is the correct answer. So here a tapering uniform, this case, and without tapering. So one case is tapering and one more case is without tapering. So in this case the D1 capital D is directly proportional. This is capital D, this is D1 D2. It's directly proportional to D1 D2 under root of D1 D2. So equal to ultimate tensile stress of a mild steel is dash the ultimate compressive stress. So mild steel asking. Mild steel means a ductile material. So ductile materials are strong in so 29, as you know, that is C. So C more than, they are strong in tensile. The maximum stress produced in a bar of tapering section is at its smaller end. So 4PL by pi D1 D2 into E for total bar. 4PL by pi DE is the, if it is bar you are considering one side. If this D is how much small, the total value will become that much big. Modulus ratio of a two material is the ratio of modulus of elasticities. Okay. This is modular ratio. Shear modulus of most material with respect to modulus of elasticity is how much? It's a B, less than half. A rod is enclosed centrically in a tube and assembly is tightened by a rigid washer. So there is a rod and there is a tube and washer. If its assembly is subjected to compressive load, then the both the tube and rod under compression. So like this, you are applying force like this from this side and this side, then both tube and rod under compression. A bolt is made to pass through a tube and both of them are tightly fitted with the help of the washer and nut. The nut is tightened, then the bolt is under tension and then the tube is under compression. Okay. Next, when a bar is subjected to change of a temperature, the deformation is prevented, the stress induced in the bar is called as a thermal stress. If a steel bar is heated from this to this and the free to expand, whenever free to expand, you always just see zero answer, no stress. And in the thermodynamics also, whenever it's free expansion, heat transfer, net heat transfer, work done, all are zero. When a bar is cooled minus 5 degrees centigrade, it will develop tensile stress. See, this is the fixed bar. Now it is heating. What will happen? It will going to hit this, it will expand, so it will be compressive force applying on these walls. Whenever you cool, it will come near, then what will happen? It will apply the tensile force. A bar of copper and steel is composite system which is heated to temperature of minus 40 degrees, and the stress induced in the bar, copper bar, will be, so it is a compressive force because copper has the more thermal conductivity. It is try to expand, but what will do, this steel is less thermal coefficient, so it will try to pull this side, so it will be compressed. Basically it will be compressed. So 38 is B. Thermal stress in a bar is, thermal stress is what formula? Alpha into T into E. So it is a directly proportional to change in length. Alpha into delta T actually. So directly. Thermal stress does depend on cross sectional area. Does not depend on cross sectional area, because in the formula there is no cross sectional area. If there is a fall in temperature of composite body, when the member having the greater coefficient of linear expansion will be subjected to compressive stress. Now its temperature is falling, not increasing, so then it will be going to under tension, not compressive stress. It will going to under tensile force, tensile stress. A thermal or temperature stress is the function of, so thermal stress is alpha T into delta T into E. So increase in temperature S, delta T, modulus of elasticity S, coefficient of linear expansion, that's alpha. Okay, yes, all of the correct. A circular bar is tapered uniformly from D1 at one end, D2 at the other end, and subject to the increase in the temperature T, the thermal stress induced is equal to, so alpha TE into D1 by D2. So this is the 43 is A. 43 is A. Which of the following statement is correct? The stress is the pressure per unit area. Pressure, not force, per unit area. Strain is expressed in mm. No, this one also wrong, this one also wrong. Hooke's law holds good up to the breaking point. No, up to elastic limit. Stress is directly proportional within the elastic limit. So this is the correct. The deformation of a bar per unit length in direction of the force is called as linear strain. Deformation of bar in that direction is called as a linear strain. Every direct stress is always accomplished by a strain in its own direction, and the opposite kind of strain in every direction at right angle to it. Such strain is known as a lateral strain. So whenever you are applying this pushes or pulling, there is some stress is applied in this direction, that is linear strain, but this body also expand, means the diameter will increase, that we call as a lateral strain. Okay, the ratio of a lateral strain to linear strain is known as Poisson's ratio. So it is indicated with mu is equal to lateral strain by linear strain. Okay, this is the formula. So basically it will get minus actually this value. Poisson ratio is the ratio of the linear strain to volumetric strain. So no, linear strain to volumetric strain, that is not a correct answer. So this is the false. So 48 is B. A steel bar of 2 mm long, this much wide and thick, is subject to pull up this much. If the same bar is subject to push up this much, the Poisson ratio of this bar in the tension will be as the Poisson ratio of bar in this in compression. So 49 is A. So always you remember, when the same bar applying the compressive force of the same force are applying the same tensile force of same force on the same bar on the same location, then the Poisson ratio of the bar in tension will be equal to Poisson ratio of the bar in the compression. If you want, you can check also. Okay, you calculate the compression and tensile, two formulas. The Poisson ratio of the steel varies from these questions they will ask in the exam. So steel, cast iron. So you have to remember. So what is the steel? It is a correct. It's a 0.23 to 0.27. Okay. Next, what is the cast iron? It's correct. So it should be 0.25 to 0.33. A bar of length L, width B, thickness T is subjected to pull of P. So now it's going to pull. Then what will happen? Its length increases, width and thickness is decreases. Length increase, width and thickness decrease. So 52 is C. The ratio of change in volume to original volume is called as volumetric strain. A bar of length L, breadth B, thickness T is subjected to push of P. Now this is going to push. What will happen? Its length decrease, width and thickness increase. So 54 is D. Next, 55. Volumetric strain is the ratio of. It's a ratio of original volume to change in volume or change in volume to original volume. Always strain means change in dimension by original dimension. Next, a rectangular bar of length L, breadth B, thickness T is subject to axial pull of P. The linear strain is given by the. So the linear strain is given by the. So that's correct. 56 is as correct. A. So P by BT into E. So how can you remember? So P by B into T is area. So P by area means stress. Stress by Young's modulus is strain. Like this you got the formula here. In a rectangular bar of length L, breadth B, thickness T is subject to axial pull of P, the volumetric strain is. So 57 is, that is C. So 1 by M means mu. So that is the linear strain. So E into 1 minus epsilon into 1 minus 2. Okay. So this is our answer. A body is subjected to three mutual perpendicular stresses of equal intensity. The ratio of direct stress to corresponding volumetric strain is known as. So stress to volumetric strain is called as bulk modulus. The relation between the Young's modulus and bulk modulus is given by the. So E is equal to 3K into 1 minus 2 mu. So from here, the mu they are considering 1 by m we can write. So you can substitute and you can calculate. In place of mu you write 1 by m, so 2 by m. So and you cross multiply and you get the k. So what you get? 3m minus 2, I think this bm 59. That is the d. So you just in place of m you write mu, in place of 1 this one you write and you get the ratio of bulk modulus to Young's modulus for a Poisson ratio of 0.25 will be. So they are asking, see, first of all there are three formulas is there. E is equal to 2g into 1 plus mu. E is equal to 2g into 1 plus mu. E is equal to 3k into 1 minus 2 mu. E is equal to 9 kg by 3k plus g. So these are the three formulas. You can apply those formulas. Now this one, bulk modulus, that is k, and Young's modulus E, and the mu they given. So which formula you have to apply? Second formula you have to apply, and they get the ratio of E by k by E. So you will get 60. Question answer is how much? that is B. So this much you have to do at least. Already I providing everything, formulas and everything. You have to just substitute and you have to get. Okay. A cube is subjected to three mutual perpendicular tensile stresses of equal intensity. The volumetric strain is equal to 1 minus 2 mu by E into 3K, 3 epsilon. So this is the A answer is the correct. So 61 is A. The relation between modulus of elasticity and Young's modulus of rigidity is given by, that's already told you this formula. In place of mu you write 1 by m and you get the G. So 62 is how much? It's A. So after you solving you get this one. The modulus of elasticity of a material is twice its modulus of rigidity. So E is equal to 2G. The Poisson ratio of the material is equal to 0 and mu is equal to 0. Then mu is equal to 0 is asking. So you know already E is equal to 2G into 1 plus mu. So you can substitute. So E is equal to 2G, then 2G is equal to 2G into 1 plus mu. 2G will cancel, so 1 will become 1 plus mu. This 1 use and this 1 minus 1 equal to mu, so mu is equal to 0 as correct. Like that you have to solve, then only you can crack the exam. So 63A. The relation between the Young's modulus and shear modulus, bulk modulus is equal to 9 kg by 3K plus G. The ratio of shear modulus G and Young's modulus E for the Poisson ratio this much. So they are asking, first formula you have to apply 2G into 1 plus mu E is equal to. So in place mu 0.24 you apply 0.4 and you get the G by E. The so this answer is how much? 65 is C. You will get C. Okay. You get C. The modulus elasticity for a given material is twice. So E is twice of modulus of rigidity. The bulk modulus is equal to, they are asking. So you just apply the bulk modulus. Third formula you have to apply this one, condition you put and you get the value. So 66 is C. So 2G by 3. Next, the Young's modulus of material is this one. So E is equal to this much. Poisson ratio mu is equal to this much. Modulus of rigidity means G is how much they are asking. So E is equal to 2G into 1 plus mu. In this formula you apply and you get the Z. So this 67 is how much? It is B, 50 gigapascal. Which of the following statement is wrong? So the bulk modulus is ratio of linear stress to linear strain. That is the wrong statement is asking. Shear stress across a plane is always accomplished by the balancing shear stress across the plane and normal to it. As it's correct or wrong? It will balance. Shear stress across a plane is always accomplished by balancing shear stress across the plane and normal to it. And normal to it not will be there, only balancing will be there. Within the elastic limits, shear stress is dash shear strain. Within elastic limits, shear stress is directly proportional to shear strain. Shear modulus is the ratio of shear stress to shear strain. Localized compressive stress at an area of contact between the two members is known as correct. You are correct. 72 is C. That is the crushing. So here one rod is there, one more rod here is there. Both side you pushing, you apply. What will become here? What will happen here? Some crushing force will come because of this compressive nature. The localized. This one you can write now. The extension of circular bar tapering from D1 to D2 is 4 PL by pi D1 D2 into E. Next, volumetric strain of rectangular bar. So that is 1 minus 2 mu into E. Next, relation between the E and K. So E and K, that is equal to 1 minus 2 mu. Relation between E and G, that is 1 plus mu. Change in length due to tensile or compressive load PL by AE. So like this you can get the answers. Next, maximum diameter of a hole that can be punched from a plate of maximum shear stress 1 by 4th of its maximum crushing stress of the punch is equals to, so it's equal to, it's C 4T. So he is saying that maximum shear stress is equal to 1 by 4th of the maximum crushing stress. Shear stress formula you know, pi by 4 d square into L, and crushing stress formula you know, pi d L, pi d into thickness. So that one you both you equate, you get the maximum diameter. Plane which carry no shear stress, the planes which carry no shear stress are known as principal. Yes, correct. So on principal plane, no shear stress is 0. When the body is subjected to direct tensile stress sigma in one plane, the normal stress on the oblique section of a body inclined at an angle theta to the normal to the section is means sigma n is basically asking, sigma n is basically asking, and that value is as correct sigma into cos square theta. So the next question you can see here, same question here, normal to the section, the body is subject to direct tensile in one plane, that here normal stress asked, here what is asking, tangential or the shear stress asking, that is sigma by 2 into sine 2 theta. Okay, in the above question normal stress on an oblique plane will be maximum when the theta is equal to, so when this theta is maximum in cos, when theta is maximum at 0 degrees, as 0 is cos 0 is 1. Okay, so 77 is A. The direct stress across a plane, principal plane, is known as a principal stress. Yes. So this one already we know, 79 we did. The resultant stress on an inclined plane which is inclined at an angle theta to the normal section of which is subject to direct tensile stress in one plane is, so direct stress in one plane is, the resultant is asking, resultant means these two are resultant is asking, that value is how much, that is the B sigma cos theta. So means under root of this one square and under root of this one square and under root of this one square, so plus, in between plus, then you get this answer because the resultant is asking. When a body is subject to direct tensile stress in a one plane, maximum normal stress across a section inclined at dash to the normal section of a plane. Maximum normal stress is asking maximum normal stress. So maximum normal stress is maximum at 0 degree. So maximum normal stress means sigma n, that is equal to sigma into sigma square into sigma into cos square theta. So theta is maximum, cos theta is maximum at 0. When the body is subject to direct tensile stress, maximum normal stress is equal to the direct tensile stress. As this is correct? Yes, it's correct. A body is subject to direct tensile stress in one plane, the shear stress is maximum. Shear stress is maximum sine 2 theta. Sigma by 2 into sine 2 theta. So when 2 theta will maximum, when theta is equal to either 45 or theta is equal to, then 90 will become, or theta is equal to 135. So this one. So 83 is B. 84. When a body is subjected to direct tensile stress sigma in one plane, the maximum stress shear stress is dash the maximum normal stress. Maximum shear stress is how much? Sigma by 2 into sine 2 theta, and this is sigma into cos square theta. When it is maximum, this value will be 1, this value will be 1. So the tensile stress in one plane, maximum shear stress is half of the maximum normal stress, because this is sigma by 2 you will get, this is sigma you will get, so 1 half. So 84 is as correct, it's a B, 1 half. Principal plane is a plane on which the shear stress is as correct, shear stress is 0. When a body is subject to direct tensile stress sigma x in one plane, accomplished by a simple strain. This one, maximum normal stress is equal to sigma x by 2 into 1 by 2 into under root of sigma x whole square plus 4 into tau of xy whole square. Correct. If it is minimum normal stress means minus will come, maximum means plus will come. Minimum normal stress is asking. Now this case, this one will come. So 87 is B. Maximum normal stress, again one plane accompanied by single maximum normal stress is given by the, again, so here what is asking, maximum shear stress, not normal stress. Here shear stress asking, so you will get maximum shear stress is, yes, correct, that is 1 by 2 into under root of sigma x whole square plus 4 into tau of xy whole square, that is 88 is D. Maximum shear stress means sigma 1 minus sigma 2 by 2. The body is subjected to direct tensile stress of this much, accomplished by the simple shear stress of this much, tau xy. The maximum normal stress will be, you apply in the first formula, this formula you have to apply. Then what you get, the answer. So you get the answer is 89 as the D. Just you do it. Just substitute in that formula. What is the formula? Sigma x by 2 plus and 1 by 2 into under root of sigma x whole square plus 4 into tau of xy whole square. In this formula you apply. So in place of sigma x you applied, this is sigma x 300, this is tau of xy, that is 200. You apply, you get the answer. In the above question, the minimum normal stress will be, so here in place of plus you write minus, so you will get the value. So how much you get? 90 is equal to A, that is minus 100 you will get. In the question 89, means this question only, the maximum shear stress. Maximum shear stress is what? Already we did, just now we found 1 by 2 into sigma under root of sigma x whole square plus 4 tau of xy whole square. In this formula you apply sigma x and tau of xy, you get the answer. So what is the answer? 91 is B, that is the 250. When a body is subjected to biaxial stress, that is direct stress, sigma x, sigma y and two mutual perpendicular accomplished by a shear stress, this one, the maximum normal stress is, so maximum normal stress, so this one will be sigma x minus sigma y whole square plus 4 tau of xy whole square. So this is the formula. Minimum normal stress, in place of plus you get the minus. Okay. Maximum shear stress, already you know, 1 by 2 into under root of sigma x, this one you will get. Now say, first formula you have to substitute maximum normal stress. This one is given sigma x, sigma y and tau of xy they given. You have to substitute and you have to get the value. So 95 is how much? D, 1400. In the question minimum normal stress. So in place of plus you have to substitute minus and you have to get the answer. So A, 400. In the same question, the maximum shear stress asking. Maximum shear stress means this formula, 1 by 2 into sigma x minus sigma y whole square plus 4 into tau of xy. Substitute, you will get the answer. So 98 is how much? C, that is 15 kilonewton per meter square. For a biaxial stress, the plane of maximum shear stress at right angle to each other and are inclined 45 degrees to the principal planes. Yes, correct. Yes, correct. So 99 is correct. 100. This is the case. Sigma x given, tau of xy given, sigma y given. Okay. So maximum shear stress asking. What is the maximum shear stress formula? 1 by 2 into under root of sigma x minus sigma y whole square plus 4 into tau of xy whole square. So just substitute sigma x minus sigma y. So sigma x is minus 40 and this is also become minus 40. So under root of minus 80 whole square plus 4 into tau of xy is 30 square. So minus 80 whole square means 8 8 is 6400 plus 9 4 is 3600. So under root of 1 by 2 is in front is there. So what you get? This is 10,000 you will get. 10,000 means outside how much will come? This is 100 square. 10,000 means, so 100 by 2. 100 by 2 means 50. So you get the 50. So 100 is C. I can solve like all the question, but it will be helpful for you if you do it. You do it that formulas already I am saying you. Just substitute in that formula. Maximum shear stress is dash the algebraic difference of the maximum minimum stresses. So maximum shear stress formula is sigma 1 minus sigma 2 by 2. It is the algebraic difference by 2. So means 1/2 of the algebraic difference of the maximum and minimum stresses. Okay, there is a more circle is given. Is asking the minor principal plane is given by. So minor principal plane. So what is the minor principal plane he is asking? That is correct. OC, C, that is the OQ. O to Q is the minor principal plane. So 102 is C. 103 is tangential stress is, that is PQ. This PQ is tangential stress. OQ is the minor principal plane. Resultant stress is yes, you are correct. That's the 104 question. That is the B, that is OP. That O to P is the resultant. You can write this is the resultant. If you draw the triangle also, this is the resultant force that you can consider. Vectors also. Radius of Mohr circle in this 2.40 is equals to. So it is how much? So radius of Mohr circle is always, so this is sigma x minus sigma y by 2. So difference of two principal planes, half the difference of two principal planes. So 105 is D. The maximum shear stress is equal to, so maximum shear stress is asking. So maximum shear stress is how much? It's what? This is what? This is maximum shear stress. So what it's basically, it's a radius. So 106 is A. Mohr circle is used to determine the stresses on oblique sections of a body subjected to the tensile stress in one plane accomplished by shear stress, tensile stress in two mutually perpendicular planes. So in all the cases we can apply actually Mohr circle. The radius of the circle, the Mohr circle radius of the circle formula is asking. So sigma 1 minus sigma 2 by that one you get, then you get the answer is this one. Okay. So 108 is C. 109. The center of the circle from y axis is taken as sigma x plus sigma y by 2. So that's 109 is B. The extension of a experiment of extremities of any diameter of a Mohr circle represents. So what it represents? The extremities of any diameter on a Mohr circle, it represents normal stress on a plane at 45 degrees. And this is the Mohr circle. Any extremity diameter, what it represents? Normal stress on plane at 45 degrees. Maximum shear stress is equal to radius of the Mohr circle. Correct. Energy stored in a body when strained within the elastic limit is known as you are correct, is known as a strain energy. But according to me, it's a resilience. Because I think here answer is given wrong. Strain energy within the elastic limit is known as strain energy. The total strain energy stored in the body is termed as, is known as, what we known as this one, 113 is A, that is resilience is saying. Proof resilience is the maximum strain energy which can be stored in a body. That's correct. Next 115. Proof resilience per unit volume of the metal is known as the modulus of resilience. That's correct. Strain energy is the energy stored in a body when strained within the elastic limit. So 116 is what? A. within the elastic limits. The strain energy stored in a body when suddenly loaded is dash the strain energy stored in the body is gradually loaded. It is twice. Because strain energy formula is what? 2 P by A into stress into 1 plus 2H by A E by L something formula is there. There is the strain energy formula. So in this one, if you apply 1 plus sigma into 1 plus under root of 1 plus 2H L something, this formula is there. So H is, if it is 0 also, 1 plus 1 2 sigma will be there, so twice it will be there. But he is asking strain energy, so strain energy what will be there? So this is the strain energy, so this double will be there, 4 times it will be there. 117 is what? D, because 2 sigma square by this formula will be there. Strain energy 2 sigma square by 2p square by AE formula is there. Resilience is energy stored in a body when strain up to can be restored in the body. So within the elastic limits, 118 is as correct. D. Already we studied here, resilience means total strain energy stored in a body is termed as resilience is saying. Strain energy stored in a body is called proof resilience. Total strain, that is resilience, so disagree. Modulus of resilience is the proof resilience per unit volume. Yes, correct. Strain energy stored in the body, sigma square by E into 2V. So that is sigma square V by 2E. So that is the 121 is C. Sigma square 121 is D. So that is the, so that's why in the previous question, in place of sigma 2 sigma you apply, so 4 sigma square you get, so that's why 4 times. The stress induced in the body when suddenly loaded is, stress is asking now time, it's a twice the stress induced body when it is gradually applied. Just now we calculated. The strain energy stored in a spring when subjected to maximum load without suffering the permanent deformation is known as. The strain energy stored in a spring when subjected to maximum load without suffering permanent deformation is known as, as you are correct, that is the proof resilience. (124) The capacity of strained body for doing work on a removal of the straining force is known as what? That's the correct. It's a resilience. Which of the following statement is correct? So 125 is D. All of these are correct. Strain energy stored in a body due to its shear stress is, so always tau square will come, so will be answer will be C. 126 is C. 127. A beam which is fixed at one end and free at other end is called, fixed at one end and free at other end is called cantilever beam. 127 D. A beam supported at both ends is not a simply supported beam. It's not a simply supported beam. False. If it is beam is supported at both ends, it is called as a simply supported beam. A beam extending beyond the supports is known as a overhanging beam. If it is beam is like this and it is beyond its supports like this, here from the support there is no beam is there, but here beyond the what is there, beam encasted at the both the ends is called as a, encasted means fixed like this, welding something, fixed beam. Beam supported one more than two supports is known as a continuous beam. Means more than one support is called as a continuous beam. Cantilever beam is one which is supported fixed at one end, free at the other end. A simply supported beam is one which is supported on more than two supports. No, that is continuous beams. Overhanging beam must overhang on both supports. No, it can be overhang on single support also. It's overhanging from this support only. This support it is not overhanging. So 134 is yeah. Next, but A is given, but that's wrong. The book. Fixed beam is one which is fixed at dash of its ends. It's fixed at both of its ends. Continuous beam is one which is supported on more than two supports. Concentrated load is one which is act at a point on a beam. So concentrated load means like this. So 137 is A. The load which act at a point on a beam is called as a uniformly distributed beam. At a point is called as a concentrated load. Uniformly distributed load may be assumed to behave like a point load. No, load at the center of gravity of the load for all short of calculation. Yes, we'll do like this. The load which is spread over the beam in which a manner that the varies uniformly over the whole beam of the length is called as a uniformly distributed load. The shear force at a point on a beam is the algebraic sum of all the forces on either side of the point. The bending momentum at a point on a beam is the algebraic sum of all the moments on either side of the beam. So 141, 142 A. Bending momentum on a section is maximum when the shear force is is 0. 143 is see when the shear force changes sign. There it is basically 0 actually. Why this is given we don't know. This is the shear force. It is changing here, means that shear force is 0 here. We can sell that one also. Shear force at a certain point on a beam changes sign from positive to negative value or vice versa. The bending moment at that point will be 0. No, it will be maximum. So false. When a load on a free end of a cantilever beam is increased, the failure will occur at the fixed end. 145 B. The bending momentum at the free end of the cantilever beam is 0. So cantilever beam, what is the bending momentum diagram? So this is the bending momentum diagram. So here 0. A cantilever beam of length L carrying a point load W at the free end as shown in the figure. Which of the following is correct? Which of the following is correct? That is, the A is a shear force diagram and C is the bending momentum diagram. So this is the rectangle, means the second one should be linear. This is a 1 degree, 0 degree, this is 1 degree parabola. The cantilever beam is loaded with concentrated load. Bending momentum diagram will be, it's a inclined straight line. So 148 is C. 148 is C. Because whenever concentrated load is there on the beam, shear force will come like a box and this one will come like a triangle. So inclined straight lines. The bending momentum diagram for a cantilever beam loaded with a uniformly distributed load will be a parabolic curve. So this one is there, so uniformly distributed. Then what will be happen? This load will be this already 0 degree parabola. So your rectangle will become like this shear force. Then this one will become like this or like this. So it is the parabola will come. load will be parabolic curve. So it's a parabolic curve. Yes, correct. So 149 is as correct. 150. Maximum bending momentum of a cantilever beam is shown in the figure lies at. So maximum bending moment of cantilever lies at the fixed end. So it is the 150 is B. By diagram also you can say where it is big. Shear force for a cantilever beam shown in the figure. So in this figure you can see the shear force is everywhere it is same. So W throughout its length. W into L na. So this one see 151 is C. W throughout its length. The shear force of a cantilever beam of length L carrying uniformly distributed load of W per unit length is dash at its free end. It's a W. Yes, it's a WL. So 152 is A. It's a 0. Shear force of cantilever beam is said. Shear force of a cantilever beam of L carrying uniformly distributed load of W per unit length dash at its free end. At its free end is 0 at its free end. Its fixed end what is there? W into L. No, W into L. Yes. 153 D. Shear force diagram for a cantilever beam of length L and in the carrying a uniformly distributed load W per unit length will be. So it will be like this is there. So it will be maximum here and it is a right angle triangle. 154 A. 155. The bending momentum of a cantilever beam of L and carrying uniformly distributed load W per unit length is dash at its free end. It is a 0. 155 is A. 156. The shear force and bending momentum are 0 at the free end of a cantilever beam if it is varies uniformly distributed over the whole section. The shear force and bending momentum is 0 at the free end of a cantilever if it is varies a uniformly distributed load over the whole length. So that is the C. 156 is C. The bending moment of a cantilever beam of length and carrying uniformly distributed load W per unit length is dash at the fixed end. So WL will be convert like this. So this is L by 2, WL square by 2. So this is D. 157 is D. 158. Maximum bending momentum of a cantilever beam of length carrying uniformly distributed load W per unit length lies at the middle of its length. Yes, maximum bending momentum where it is lies at the middle of its length. No, its maximum bending momentum is lies at fixed end. So 158 is B. By diagram also you can say here is less compared to here. The shear force diagram for a cantilever beam of L carrying uniformly gradually varying load from 0 at one end and the what is saying 0 at one end like this is carrying load fixed at the other end, W per unit length is the other end is. So this is already linear, so it will become parabola. So this is the parabolic curve. So 159 is D. 159 is D. 160, the last question of this video. So like this we will convert in these three parts, total 480 questions. The bending momentum diagram for a cantilever beam L and carrying gradually varying load at 0 at the free end, W per unit length at fixed end is parabolic curve. So bending momentum is parabolic but second degree parabolic curve. So 160 is A. That is the parabolic curve. Now see, now in this video we finished all the 160 questions. Like this we will finish all the 480 questions. It will be very helpful for you. Now this video is approx of 1 hour. So in this 1 hour you are finishing Like this, in 3 hours you will finish all the RS Kurmi strength of materials question. So like this, it will be a test for you. Like that, once you do the test, strength of materials like this, one chapter, the morning you take give some time for one video, at the evening you give one video. Like that you finish. You have to plan and you have to finish. You don't have to waste your time, because the time is very precious now these days, because this is the young, you now you have the age for to do hard work and everything. Your body is supporting, so you have to do the hard work and you have to finish all the things, whichever is a need for your exam. Whatever practice you can do it before the exam. Whatever plans you can do, plan before the exam. And all the videos and all the even the whatever the test series, whatever is there, that one you finish. And try to gather this information as fast as possible. So that's why I'm providing this video. You can increase your YouTube speed and you can finish this video very fast also. So this will be very helpful for you exam point of view. So if you like my channel, so just subscribe, so that you can all the videos, whatever I am